I think we're good to get started here. Just as a reminder of what's been going on, Section 9.1 was an introduction to sequences and series. 9.2 focused specifically on arithmetics. 9.3 specifically on geometrics. 9.4 is specifically on quadratics. Tomorrow will be mixed review of the 3 types, plus other types of patterns as well that you don't necessarily have to have formulas for, that would fall under kind of a number sense, like inspection type of category. And then the quiz on this stuff will be on Monday. So that's where we are, where we're headed with this particular set of topics. Any problems or questions before we get going? All right, we only have the 2 sets of examples to do here. We should get through this rather quickly. That'll leave plenty of time to ask any questions you might have from the last 2 homework assignments, and we're going to jump on tonight's homework. All right, as a comparison point, what we're going to do is go back to an arithmetic sequence example. So for this first sequence, we have 3, 5, 7, 9, 11, 13, 15. So it's going up by 2 each time to get from one term to the next. So we have that D value to be 2. We could classify it as arithmetic. And if we wanted to write an explicit formula for this, using the method that I showed you guys, whatever that common difference is the coefficient of your variable. If there was one more term in front, what would it have to be in order to make this true? We get a to the n is equal to 2n plus 1. With any of these sequences, whether they're arithmetic, geometric, quadratic, or otherwise, you can always check to see, does the formula that you write really work? So, for example, that's the 1, 2, 3, the 4th term. If we plug a 4 in for n, we better get a 9 back again. So 2 times 4 is 8. 8 plus 1 is 9. We can be pretty confident we wrote the formula correctly. Then once we have an explicit formula, we can find any term we want within that sequence. All right, now the comparison to the new stuff here. An alternative way of thinking about these plus 2s is what we're going to do is consider that set of numbers our first order differences. So what's happening here is we have a constant first order difference, which means when we do this set of subtractions going across, that number is the same. Okay, now in contrast, this pattern right here, 3, 5, 8, 12, 17, 23, 30. If we do the first order differences, from 3 to 5 is plus 2. 5 to 8 is plus 3. 8 to 12 is plus 4. And we got plus 5, plus 6, plus 7. If we take the difference of the differences, which means the second order differences, there to there is plus 1, plus 1, plus 1, plus 1, plus 1. That constant second order difference is what allows us to classify this as a quadratic pattern. So constant first order differences means it's linear. Constant second order means it's quadratic. All right, everybody okay with that? All right. Now, once we identify it as quadratic, what rules do we have as far as finding an equation to model it? It turns out that getting an equation by paper pencil calculations is or can be rather cumbersome. If it's a nice clean pattern, like they're all the perfect squares or something like that, where it's like kind of obvious by inspection, then we don't really need any specific rules. But once we get beyond the obvious, for example, this one here, we're not going to do the paper pencil calculations in order to get the quadratic equation. What we're going to do is use the calculator for that. All right, if we're going to use the calculator, one of the things we need to remember is unless you're told otherwise, you're always assuming starting with an n is equal to 1. So this is the first term, second term, third term, etc. The other common beginning point is to begin with an a sub 0 or an n is equal to 0. There needs to be something specific within the instructions or specific within the problem in order to go that route. So here's how we're going to handle this. Take out your graphing calculator. If you need one, grab one from the class set. I'll pause for a minute to allow you to do that. Right, going to go to stat, edit, and in L1, we're going to put the number of the term. So we already said we need to start with 1. And for this pattern, we have 1, 2, 3, 4, 5, 6, 7 terms. So we're going to put in 1 through 7 in L1. And I apologize for the glare with this. Sometimes it's there, sometimes it's not. And then in L2, we're going to put in the terms themselves. So 3, 5, 8, etc. And we're going to quit out of there. Stat calc. And we've already identified that we can model this with a quadratic equation because it's a quadratic sequence. So we're going to choose quad reg. Your X list is going to be the number of the term, which is L1. Your Y list is going to be the term itself, which is L2. Frequency list, we're leaving blank. And if you're going to be making any kind of predictions or doing anything else with this equation, you're probably going to want to store it. So alpha F4 is the shortcut. Put it right in Y1. And then calculate. So that's how we get our formula using the calculator for this particular sequence. Okay, I'm going to go to table set. Started at 1, put on auto. That means it's going to start with an n value of 1, go up by 1, and then automatically fill in. And we can see in the table here, the y values for the first 7 should match what we already typed in. If they don't, something went wrong, horribly wrong. And then if we wanted to make any predictions, we could make them right from this window. So say, for example, we wanted to know what the 20th term of the sequence was, 212. Good. All right, a little connection back to other things that we've learned. I'm going to rerun that quadratic regression. Now, when we did most of 4 of the 5, I think, chapter 3 curve fitting types of problems, as long as our diagnostics were turned on, we got an R and an R squared value. Okay, R and R squared are the byproduct of the algorithm that the calculator uses in order to create those curves of best fit for, what did we do? Logarithmic, power, exponential, and is there another one in there other than logistic? I forget. But anyway, as far as what we did with them, we used them to help determine how well did that curve fit that particular data set. And when we did the logistic curves did not give us an R or an R squared because it was a different algorithm that produced that equation. Okay, with the quadratic regression, yet again, it's a different algorithm that produces an R squared but not an R. It's still, the closer that is to 1, the better it fits. And since we need an equation to fit all that data, it's not like close enough with this. We need an exact equation that better be 1. So if you do one of these problems and your R squared is something other than 1, something went wrong somewhere, most likely you probably typed the data in your calculator wrong, or you incorrectly identified it as being quadratic when it's really not. All right, good with all that. All right, second slide. What they're giving us to start with here is a recursive formula, or implicit. Recursive and implicit mean the same thing. And with these guys, recall that they have to give you some beginning point for the sequence and then give you some rule of how to move from one term to the next. Okay, these can be a little bit more confusing with quadratics than the linear or the geometric were, because the n is in two different places. It's like working as the subscript here, and it's also working as the what we multiply by there. So for some students, it becomes a little bit trickier sometimes to mental math your way through this. And for me, I kind of like to write this stuff out. I have a tough time like keeping track if I don't do that. So this is the strategy I like to use. Well, they're specifically telling us for n is equal to 1 that it's 0. Now, for n is equal to 2, what I'm going to do is take that blank formula, plug in 2, plug in 2, plug in 2. So a sub 2 is a sub 1 plus 2 times 2. That 2, because it's part of that formula, that 2 because it's the second n. So the first term plus 4 will be the 0 plus 4 is 4. And then for n is equal to 3, I'm taking the blank formula, plugging in 3, plugging in 3, plugging in 3. So a sub 3 is a sub 2 plus 2 times 6. So the second term plus 6 gives me that term. And then one more time, blank formula. If I want the fourth term, 4 goes in here, here, and here. So a sub 4 is a sub 3 plus 2 times 4 gets me 18. And then 2 more to nicely fill up the page. All right, so looking at the sequence now, again, unless you're told otherwise, we assume we start with n is equal to 1. So we have 6 terms. These are the actual six terms. If you check the first order differences, plus 4, plus 6, plus 8, plus 10, plus 12. That's not constant. Therefore, we can rule out this is not a linear sequence. If the second order differences are constant, plus 2, plus 2, plus 2, plus 2, then we can safely classify it as a quadratic. Okay, once we classify it as a quadratic, if we want to get an explicit formula, we're going to do it as a calculator-driven problem. So one more time through the keystrokes. Go to Stat Edit. I'm going to clear out L2. I can still use at least part of L1. L1 represents the number of the terms. We're going 1 through 6. So I could just get rid of that 7. And then in L2, put in the terms themselves. Yes.
I accidentally deleted the whole L2 thing.
Okay. Go to Stat. And then the Setup Editor should be the last choice. Choose that. And I think you have to enter one more time, and it says Done.
Yeah.
And then if you go back, deleted list should be there. Did that fix it?
Yes.
Okay. Anybody else having any technical issues up to this point? Stat Edit. Did I finish putting that list in? Yeah. So after the list is in, quit out of the list. Stat Calc. We're doing a quadratic regression equation. We're doing quadratic because we have the constant second order differences. X list is the number of the term. Y list is the term itself. Frequency list, we want left blank. If you're going to do any kind of calculations or predictions or anything with that, alpha F4, store it in whatever place you want to store it in. Calculate. So we get 1n squared plus 1n minus 2 is the quadratic equation that models this sequence. As a check, that r squared better be 1. If the r squared is not 1, then something went wrong somewhere. So if you want to make a prediction, for example, what would be the 10th term of the sequence? Go to your table. Oh, right there. 10th term, 108. Good. All right. With the arithmetic sequences and the geometric sequences, The other type of problem that we did for each of those had to do with summing up however many terms you wanted to sum up within a sequence. We're not going to be doing that right now with the quadratics. There are formulas for summing up quadratic sequences, but they are rather on the cumbersome side. The stuff that we're going to start on Tuesday is significantly more efficient when it comes to summing up quadratic sequences, and we're going to deal with that then. So as far as what you're responsible for from this section, number one, can you classify a sequence as being quadratic or not? And you're going to do so by looking at constant second order differences. Okay, once you classify it as being quadratic, can you use your calculator in order to get the equation that models it? And then, although we didn't formally do it on here, once you have the equation, use that to predict whatever term you want to predict within a sequence. Yes?
Are we only responsible for like identifying linear to quadratic? Like we won't do like predict or
Hang on to that thought 1 second. Let me wrap up what we have to do with quadratic, and I'll connect back to that. All right, the other thing that you're responsible for as far as quadratics, can you generate the sequence from an implicit or a recursive formula? And then once you have that sequence, then it connects back to the stuff we talked about on the previous slide. All right, we good with that? All right, now to your question, as far as what types of sequence you're responsible for, the specific ones are arithmetic, geometric, or quadratic. If it's something other than those three, we're just, in terms of classifying and giving it a name, it's just other. Okay, there are going to be other types of patterns that are on the quiz on Monday, but you're not responsible for naming them. You're just responsible for, like, numerically, like, finding missing terms of them, and that's going to be stuff that's on tomorrow's worksheet. That answer that? All right. Those of you at home, any problems or questions on this, stay on. Other than that, you guys can leave Google Meet. All right, for you guys, any problems or questions on the last couple homework assignments, this is the time to ask. If you want to get a jump on tonight's homework, the book is there. You can take a picture of the pages. We are more or less done for today.
So, like, is this really the only method to, like, identify what kind of sequence it is? Like, as far as, like, quadratic goes, you just look at the, I think you, like the,
Well, there are other
like
types,
the
like
first order
in terms of building off of what we did today.
yeah,
If you have a constant third order difference, then it would be a cubic.
Yeah.
Constant fourth order difference would be quartic.
Yeah.
There are other types of patterns that exist out there that are not in that, like, polynomial form.
Yeah.
Like you could have like a logarithmic sequence. I mean, and then once you identify, like, okay, it's this type of sequence, then there are certain rules and formulas you can use specific to that type.
Yeah.
But as far as ones that we're examining in detail, these three are it.
is it just visual inspection too? Like, that's what it is.
Yeah, well, that's what tomorrow is going to be. Tomorrow is going to be these three mixed in with visual inspection.
Yeah.
And with the visual inspection, if it's like write a formula, it'll be multiple choice.
Yeah.
Or it'll just be, okay, what's the next term? So whatever the number pattern is, regardless of category it fits into,
Yeah.
at this stage of the game as an 11th grader in an advanced math class, you should be able to figure out what number comes next.
Yeah. All right, cool. Thank you.
What's up?
I'm not going to be in stat today because we're leaving early.
Okay,
Go.
we are doing a simulation. And actually, there's already a video up and posted with all the worksheets.
Okay.
So you can just look there and you'll be all good.
Are the worksheets like online or something?
Well, actually, it's not even an assignment. It's just like the worksheets that are in the video are posted there.
All right. Thank you.
But you know what? I can give you hard copies. You don't have to print those out. That's silly.
What's the simulation on?
Gift certificates.
I figured out the other day that in your calculator you can do like card simulations and dice simulations and stuff like that.
Yeah, well, not all calculators have those same programs. Some have them and some don't.
Yeah.
As far as why that may be useful, if there is an AP question that's expecting you to be able to like answer something using regular probability, but you're not really sure how, if you can run a quick simulation, it might be, the results of the simulation might be close enough
Yeah.
to answer the question without really knowing it the right way. All right, so. All right, so this is the actual problem for the simulation. And then these are the three ways you could run it. Remember, for AP purposes, you'd be expected to be able to design one using technology, random number tables, or tactiles. This one requires a long time to do it well, especially when there's like 8 people in our class. So we're only going to do a couple quick simulations. So this would be how you would like organize the work from the calculator. And this is a computer generated output. And then this is how you could answer the question based on that.
Thank you.
You're welcome. So is Landon's not going to be there either? Do you see him before?
Yeah.
I'm sorry, I could have given you 2 at once here. I don't know if he's quite as motivated as you in terms of actually keeping up with this, but at least he can go film if he wants it.
The golf, we tee off at 3:00 at Bailey and they're making us leave at 12:30. I don't know.
That might be the only available bus to get you there.
Yeah, maybe.
Oh, she's in his bathroom.
Yes.
I'm just like reviewing the worksheets and stuff, but I remember asking like about this, and you just said that that's kind of just there for like a reference to like know what you're doing, but like it's doing ace of k plus 1 equals 2 ace of k plus 1. So like looking at, I'm like, oh yeah, I'll find ace of 2, but isn't ace of 2 just doesn't like turn into ace of 3 because it's like 2 plus 1? Or I don't know why like I can't.
Well, sometimes these can be tricky, which is like, so we know ace of 1 is 5. There's no doubt about that.
Yeah.
Okay, we need to figure out now what ace of 2 is.
Yeah.
So I'm going to write this right below it so it's easy to like trace the path here.
Yeah.
So that means we have to plug 2 in here. So that means that this is going to be oh, this is going backwards from the other one. Okay. So we need ace of 2. So that means k must be 1 here. So that means ace of 2 is 2 ace of 1 plus 1. So whatever this is, that's 1 more than that.
Okay.
So actually to find a second term, we have to use k is 1 in terms of plugging it in here. So this is 2 times the previous term plus 1, 11. And now for ace of 3, that means we want this whole thing to be a 3, which means that has to be a 2.
So you just like kind of just basing it off of like what you need. Like,
Yeah.
I don't know why I'm getting. So I see like k plus 1. I'm like, oh, it's a term after. You know what I mean? Like it's gonna be.
Well, you could do this same formula. Could be ace of k is equal to 2 ace of k minus 1.
Will you like presented
Plus
something
1.
like that? Like will we see something like that on like the quiz where it's kind of like it gives?
Well, it could be either way. I mean,
Okay,
either
yeah.
one is fair game.
Yeah.
Basically, the way you would read this would be, okay, whatever ace of k is, ace of k minus 1 is the one that came before it.
Yeah.
Whatever ace of k is, ace of k plus 1 is the one that follows it.
Okay.
So whatever way you need to kind of tweak your thinking with that.
Yeah. All right. Thank you.
You're welcome. Never stop the recording.